In the last video, I mentioned the different behaviors of some of the different layers of the planet and how their physical properties differed. And I thought this would be a good time to take a bit of an aside to talk about phases and phase diagrams. And we're going to need these phase diagrams as we go. So try to digest these things as much as possible for here, but don't sweat being able to fully interpret phase diagrams. There are plenty of folks in upper level geologies and chemistry courses that still have trouble with that. Yes, there are more than 4 states of matter. For this course, we can just consider the 4 most common ones: the solid phase, liquid phase, gas phase, and then plasma. I often see misconceptions about what plasma is, what this state of matter means. So just to make sure, think of a gas. Let's just think of a helium gas. So helium's really simple. It's just 2 protons, some number of neutrons, and an electron cloud around that. Individual atoms. It's the reason I'm using helium as noble gas, and it doesn't make bonds. So that's all it is as a gas. But if you apply enough energy to it, you strip off the electrons, or at least some of them. And so what you have is an ionized gas that can conduct electricity. So that is the definition of a plasma. It's an ionized gas. Gases are what you expect them to be, and we can delve into that more if you want. I would point out here at the bottom that both gases and liquids are considered fluids. So those gases on the previous slide, they will expand to fit the shape and volume of whatever they're contained in, whether if you have them in a 1 liter glass to start with, sealed, or if you open that and they expand out to fill an entire room. So their volume changes and their shape changes to match whatever they're in. So contrast that to a liquid where it does change shape if you dump it out of a container. It doesn't change volume. So if you dump out a liter of water on the floor, it's going to spread across the floor, a very different shape, but it's still a liter of water. It doesn't change the volume of it. So that's our simplest definition of a liquid. There's more going on with how forces are arranged and surface tensions, but we won't need all that stuff. And solids. Okay, so this is where it starts to get a little different. For the most part, solids are what you think of them as. And the simplistic definition that you've probably heard before is that it has a definite shape and a definite volume. So to return to our analogy from before, if you dumped that liter of water out, it would still be a liter, but it would spread out to take a new shape. And where if you had a 1 liter block of iron and you dumped it out, it would still be a liter and it would still be a block of iron. It wouldn't care that it was no longer contained in something. It would maintain its shape. That's because if we took that iron, let's say it's in a cubic shape to start with, so it's an iron cube, right? It's a solid. But you could hammer on that iron to turn it into a new shape. So it doesn't always maintain its shape. Does that mean that it's not a solid? No, it is a solid. So how much does it have to resist changing its shape to be a solid versus a liquid? And then we'll get into another idea of a problematic area, that whether a glass is a liquid or a solid. I'm going to come down solidly, no pun intended there, on the side of a glass being a solid. We're going to differentiate them into crystalline versus amorphous solids. And a glass is just going to be an amorphous solid, but still a solid. Okay, phases of matter. And I often hear the term phase of matter and the term state of matter used interchangeably, and it's not precisely correct. So you can have states of matter that are also phases, but you can have more phases involved. And especially in the case of geology, we're going to see multiple phases of solids. So a precise definition would be a homogeneous substance that has a well-defined set of physical and chemical properties. So that means that it is something distinct from a different phase. Now, a less and maybe more usable, but I can't guarantee that it'll always hold up, but another usable version of the definition might be that it's physically separable. So if you can separate out your aragonite from your calcite, both of them are the same solid with the same chemical formula and everything else, but they have different physical and chemical properties. And maybe I can clear up some of this with an example. So let's talk about H2O system. So we know that you can have vapor phases, gas phases, like steam. You can have liquid phases, like liquid water that you're used to. And then solid, like ice. But turns out that there's not just one kind of ice. There are many kinds of ice. I'll show you that on the next slide. And the different solid kinds of ice behave differently. For instance, some of them are denser than water and would sink. They're more stable under a higher pressure, so you're not going to have them where they could be involved with floating on liquid water. But it would be a very different world if they did not. A phase diagram, and you're going to see phase diagrams until you are completely sick of them. I'm going to use them a lot, but they explain a lot of what's going on. So this is a phase diagram for H2O system. So you're used to the vapor form down here. It's at high temperature along this horizontal axis at the bottom, and it's at low pressure, both the right side and the left side vertical axes are pressure. So low pressure like you would expect in the atmosphere, and fairly high temperatures. Not super high, but it would still be a gas. Then if you put it under more pressure, it's in a liquid phase, or under less temperature, you can get to this first solid phase, which is the 1H. The H is hexagonal here, the ice 1 phase. But you see that there are multiple other ice 2, there's a 3, 4, and 5 down in here, 7, 8, 10, 11. So a bunch of different solid phases of ice. So how to read one of these diagrams. So the way it works is you think about the pressure. So we'll start from 1 atmosphere, which is about 100,000 pascals of pressure over here, and you intersect that with your temperature. So let's say 25 C, that's about room temperature, right? So this is in K, so we'll have to add, so it's going to be about 300, right? So at about 300 K and about 100,000 kilopascals, we would encounter liquid water. Well, that's fair. We would expect liquid water at room temperature conditions. And that's what we would find. Another example is the carbon system. So you may have heard of this before, of diamond and graphite being both just carbon. They are pure carbon. So what differentiates a diamond from just the graphite and an old school pencil? right? They're exactly the same chemically, but they are different phases of minerals. So at very low pressures, like at the surface of the Earth, graphite is stable. So if you look down here at less than 4-ish GPa, so that is metric units for billions, the G as in gigapascals. So less than like 4-ish gigapascals, and most temperatures that we'll talk about, then graphite is the stable form of that mineral. But if you increase pressures, like if you put it down in the deep mantle or anywhere near the core, diamond is going to be more stable than graphite. So your graphite would turn into diamond. All you got to do to make your pencil lead into diamond is shove it down into the deep mantle of the Earth, which you can't actually do. But if you could, you'd make diamond out of all of that. And of course, if you maintain those pressures, but you heat it up enough, you'll actually liquefy your diamonds. You'll actually melt them. So this demonstrates how you can have different phases